Inductive kick refers to a transient surge of voltage and current that occurs when an inductive load, such as a motor, transformer, or solenoid, is suddenly disconnected from a power source. This surge can cause a loud humming noise and can potentially damage electrical equipment. Understanding the causes, consequences, and solutions related to inductive kick is essential for maintaining the reliability and safety of electrical systems. Firstly, let's examine the causes of inductive kick. Switching on or off inductive loads can generate this phenomenon. Opening or closing circuit breakers or fuses can also lead to inductive kick. Sudden power outages are another potential trigger. Finally, faulty wiring or connections can contribute to the problem. Secondly, let's consider the potential consequences of inductive kick. Arcing at contacts is one possible outcome. Insulation breakdown can also occur, potentially leading to short circuits or other failures. Equipment damage is a significant concern as the voltage surge can stress and degrade components. Lastly, transients that can interfere with other electrical systems are possible, disrupting their operation. Thirdly, let's explore some solutions to correct inductive kick. One effective approach is to use surge suppressors. Surge suppressors absorb excess voltage and dissipate it as heat, reducing the magnitude of the inductive kick. Another solution involves installing line reactors. Line reactors are inductors that are connected in series with inductive loads. They limit the rate of change of current and reduce the magnitude of the inductive kick. Snubber circuits can also be employed. Snubber circuits are passive networks that consist of a resistor and a capacitor. They reduce the inductive kick by absorbing the transient energy. Proper rating and sizing of circuit breakers and fuses is crucial. Oversized circuit breakers or fuses may not trip quickly enough to prevent damage from inductive kick. Ensuring proper wiring and connections is also important. Loose or poorly connected wires can increase the inductance of the circuit and worsen the inductive kick. Finally, consider using soft start or soft stop devices. These devices gradually increase or decrease the current to inductive loads, reducing the magnitude of the inductive kick. Inductive kick can manifest in various ways and present challenges in different electrical systems. Addressing inductive kick is crucial for preserving the lifespan and performance of sensitive electronic equipment. The humming noise that is heard is magnet restriction of the components, perhaps the transformer or choke, as the magnetic field varies at twice the line frequency. There are some additional considerations to take into account when dealing with inductive kick. Firstly, consider the specific application. The best solution for mitigating inductive kick will depend on the specific characteristics of the electrical system and the inductive loads involved. Secondly, assess the risk. Determine the potential consequences of inductive kick in the specific application. This will help prioritize the implementation of appropriate mitigation measures. Thirdly, implement a multifaceted approach. A combination of different solutions may be necessary to effectively mitigate inductive kick in some cases. Fourthly, regularly inspect and maintain electrical equipment. This can help identify and correct potential problems that could contribute to inductive kick. Fifthly, use appropriate grounding techniques. Proper grounding can help reduce the magnitude of transient voltages and currents. Sixthly, shield sensitive equipment. Shielding can help protect sensitive equipment from the effects of inductive kick. Seventhly, monitor the performance of electrical systems. Monitoring can help identify potential problems early on so that it can be addressed before they cause damage. Eighthly, use appropriate overvoltage protection devices. Overvoltage protection devices can help protect electrical equipment from damage caused by inductive kick. Ninthly, consider using a power conditioner. A power conditioner can help smooth out voltage fluctuations and reduce the magnitude of transient voltages and currents. Tenthly, consult with a qualified electrician. An electrician can help assess the specific needs of the electrical system and recommend the best solutions for mitigating inductive kick. The key to understanding the magnitude of an inductive kick is the energy stored in the inductor. The energy stored in an inductor is equal to 1/2 times the inductance times the square of the current, or 0.5 times L times I squared. Inductance is measured in henries and current is measured in amps. The inductance is determined by the number of turns of wire, the core material, and geometry. The current is determined by the applied voltage divided by the impedance. The impedance includes any resistance. The faster the current stops flowing in the inductor, the larger the inductive kick will be. A switch or relay that quickly disconnects the inductor will cause a very fast change in current. The voltage generated tries to maintain the same current flow and can generate a voltage many times the original voltage. An ideal inductor has no resistance, which means the voltage and current are 90 degrees out of phase. A real inductor has some resistance, but is still largely inductive. When the current is stopped quickly, the voltage rises to try and maintain the current. This voltage can easily exceed the breakdown voltage of the components in the circuit, causing damage. The larger the inductance and current, the larger the voltage generated. One very common example is an automotive ignition coil. A 12-volt source is connected to a coil through a switch. The switch is rapidly turned off and on by the engine to create a high voltage pulse that is then used to ignite the fuel in the engine. The high voltage is generated by the rapid change in current when the switch is opened. The coil in an ignition system is designed to create a voltage high enough to create a spark across the spark plug cap. Another example of a place where inductive kick can be problematic is when switching large motors. Large motors can have a significant amount of inductance, and when they are switched off, they can generate a large inductive kick. This can damage the motor, the switch, or other equipment in the circuit. Surge suppressors are often used to protect equipment from inductive kick. Surge suppressors work by clamping the voltage to a safe level. This prevents the voltage from rising too high and damaging equipment. Line reactors are another way to protect equipment from inductive kick. Line reactors work by slowing down the rate of change of current. This reduces the magnitude of the inductive kick. Snubber circuits can also be used to protect equipment from inductive kick. Snubber circuits work by absorbing the energy from the inductive kick. This prevents the voltage from rising too high and damaging equipment. Proper wiring and connections can also help to reduce the magnitude of inductive kick. Loose or poorly connected wires can increase the inductance of the circuit and worsen the inductive kick. Soft start or soft stop devices can also be used to reduce the magnitude of inductive kick. These devices gradually increase or decrease the current to inductive loads, reducing the magnitude of the inductive kick. When dealing with inductive kick, it is important to consult with a qualified electrician to determine the best solution for the specific application. A qualified electrician will be able to assess the risks and recommend the appropriate mitigation measures. Also remember that the humming noise may be more than inductive kick, especially if it is related to the power line frequency. Magnetostriction is a property of ferromagnetic materials that causes them to change shape when subjected to a magnetic field. This phenomenon can occur in electrical equipment such as transformers, motors, and generators, where alternating magnetic fields are present. When the magnetic field oscillates, the material expands and contracts, producing vibrations that can be heard as a humming noise. The frequency of the humming noise is typically twice the frequency of the alternating current flowing through the equipment. For example, in a 60 Hz power system, the humming noise will be at 120 Hz. The intensity of the humming noise depends on several factors, including the magnitude of the magnetic field, the properties of the ferromagnetic material, and the design of the equipment. In transformers, magnetostriction is a major source of noise. The core of a transformer is made of laminated steel sheets, and the magnetic field causes these sheets to vibrate. The vibrations are transmitted to the transformer tank, which radiates the noise into the surrounding environment. In motors and generators, magnetostriction can also contribute to noise. The stator and rotor of these machines are made of ferromagnetic materials, and the magnetic field causes them to vibrate. The vibrations are transmitted to the machine frame, which radiates the noise into the surrounding environment. There are several ways to reduce the noise caused by magnetostriction. One approach is to use materials with low magnetostriction coefficients. Another approach is to design the equipment to minimize the magnetic field intensity. Additionally, vibration damping materials can be used to reduce the transmission of vibrations to the surrounding environment. In summary, inductive kick is a transient voltage surge caused by the sudden interruption of current in an inductive circuit. It can be mitigated by using surge suppressors, line reactors, snubber circuits, proper wiring practices, and soft start or soft stop devices. Magnetostriction is a phenomenon that causes ferromagnetic materials to vibrate in the presence of a magnetic field, producing a humming noise in electrical equipment. The magnitude of the inductive kick is determined by the inductance and the current flowing through the inductor. The faster the current changes, the larger the inductive kick will be. Surge suppressors, line reactors, and snubber circuits can be used to protect equipment from inductive kick. Surge suppressors work by clamping the voltage to a safe level. Line reactors work by slowing down the rate of change of current. Snubber circuits work by absorbing the energy from the inductive kick. Proper wiring and connections can also help to reduce the magnitude of inductive kick. Loose or poorly connected wires can increase the inductance of the circuit and worsen the inductive kick. Soft start or soft stop devices can also be used to reduce the magnitude of inductive kick. Magnetostriction can be reduced by using materials with low magnetostriction coefficients, designing the equipment to minimize the magnetic field intensity, and using vibration damping materials. Finally, it is important to consult with a qualified electrician to determine the best solution for mitigating inductive kick and magnetostriction noise in a specific application. These concepts are intertwined in the electrical engineering world, and understanding them is crucial for maintaining reliable and safe electrical systems. When applying surge suppression, you will want to consider several things. One is the maximum continuous operating voltage, or MCOV. The MCOV is the maximum voltage that the surge suppressor can withstand continuously without degrading. It should be at least 15% higher than the normal operating voltage. The voltage protection rating, or VPR, is the maximum voltage that the surge suppressor will allow to pass through to the protected equipment. It should be as low as possible, but still high enough to avoid nuisance tripping. The surge current capacity is the maximum surge current that the surge suppressor can withstand without failing. It should be high enough to handle the expected surge currents in the application. The response time is the time it takes for the surge suppressor to begin clamping the voltage. It should be as short as possible to protect the equipment from fast rising surges. The let-through voltage is the voltage that the surge suppressor allows to pass through to the protected equipment during a surge. It should be as low as possible to minimize the stress on the equipment. The energy absorption capacity is the amount of energy that the surge suppressor can absorb without failing. It should be high enough to handle the expected surge energy in the application. When considering line reactors, understand that line reactors are inductors that are connected in series with the load. They help to limit the rate of change of current and reduce the magnitude of voltage transients. Line reactors are typically used to protect equipment from voltage sags, voltage swells, and other power quality problems. Line reactors are rated in henries, which is a measure of inductance. The higher the inductance, the more effective the line reactor will be at limiting the rate of change of current. The size of the line reactor should be chosen to match the load requirements. A line reactor that is too small will not be effective, while a line reactor that is too large can cause voltage drop and other problems. When considering snubber circuits, a snubber circuit is a network of resistors and capacitors that is used to suppress voltage transients. Snubber circuits are typically used to protect equipment from inductive kick, which is the voltage transient that occurs when an inductive load is switched off. Snubber circuits work by absorbing the energy from the voltage transient and dissipating it as heat. Snubber circuits are typically placed in parallel with the load. The resistor in the snubber circuit helps to damp the voltage transient, while the capacitor helps to store the energy from the voltage transient. The size of the resistor and capacitor in the snubber circuit should be chosen to match the load requirements. A snubber circuit that is too small will not be effective, while a snubber circuit that is too large can cause excessive power dissipation. All of these considerations together will help reduce the likelihood of inductive kick and any humming noises that can arise.